Well, I think it's time to get started, so I'll dive in here. I mean, it was time to get started about about 10 minutes ago. But I think people have other classes, other parts of campus or something. All right, so let's see if this will. Man, that is that is too tiny, isn't it? Yeah. I was gonna try to just look at my solutions on on this Elmo thing here, but obviously there has to be some kind of zoom function. Huh? Ooh. Yeah. Guess that's okay. Can you guys see that okay? So, problem 51 here was to calculate the derivative f prime of a directly from the definition, right? So, what did I do? So, there must be a little smudge on. I need to find a lens cleaning cloth or something here. That better? Hey, actually, you know what? It might just be my eyes. No, that's fuzzy. Maybe it's my paper. I don't know. Anyway, so to calculate the derivative at a, we calculate the limit of the difference quotient, right? So for this function, 2x squared minus 3x plus 8, I put in f of x. I have f of a over here. And then we do the algebra, right? Cancel 8s. And then what? I factored this into x minus a times x plus a. And then you can see you've got an x minus a factor here and here. So we can cancel it with the x minus a downstairs. And we're left with this. Then take the limit as x goes to a. We get 2 times a plus a minus 3, which is 4a minus 3. There you go. That's the derivative of f at a. All right? And you know, again, calculating directly from the definition of the. Then the second part of the question asks us to find the equation of the tangent line. I point out here the 16 is a typo. That should be 13, because if we plug in minus 1, we get, you know, let's see here, 2 minus a minus 3, which is 2 plus 3, which is 5. 5 plus 8 is 13. That should have been 13, not 16. An error?
When I did quadratic formula, gave an error.
Why would you do? But why would we? Oh, you mean quadratic formula?
I mean,
oh, you're saying when you plug in the, you couldn't get the 16.
yeah.
Yeah.
Same error.
Right. That's good. That's good. Now, when something like that happens, you should email me. You know, so I can tell the rest of the class. I think, what's that?
So my thinking was like, actually, maybe it was just part of the problem, you know.
No. That's not the case. It's just an oversight on my part. Now, I think I meant to make an announcement to you guys about this, but in my defense, many people are not reading announcements, so what difference does it make? What's that? Yeah. No, I was telling people this morning, we have a test Friday, and we had a quiz Monday, and this was news. So, but I do mean to announce that kind of correction by announcements. I just, you know, I forget things sometimes, and my apologies. If you ever have a question about, like, whether or not the homework problem makes sense or something, don't hesitate to email me. I really don't mind. Anyway, with that correction made, you know, we define the tangent line to be f of a plus f prime of a times x minus a. That's the equation. Y equals to that is the equation of the tangent line. So in this case, we have a equals to minus 1. That was given in the problem. And f of minus 1 is 13. And f prime of minus 1, when you plug it in, is minus 7, right? So there it is. That's the equation of the tangent line right there. Yeah? Question? You got this one. See, you can do it. I mean, you don't want me to look? No, that is exactly what's on your paper. And you also have the limit. So that's good. That's good. All right, let's move on here. That was problem 51. Problem 52. What were we supposed to do here? We were supposed to, what? Calculate the derivative directly from the limit definition of the derivative. This time we've got 3x cubed minus 3x squared minus 45x. Sorry, this thing is fuzzy. Jeff, I'm in. Oh well. If you're not here, my apologies. This camera does not play well with this projector. Nothing I can really do about it. Anyway, those of you who are here can read this. So we have f prime of a, so I put in f of x minus f of a, right? And then cancel things which can be canceled. Is there anything? Well, nothing really cancels this time. So then I looked at this and I went, I'm not liking this approach for this problem. So I said, all right, I'm going to cut and run. They'll try the other way, see if it works better. So h goes to 0, f of a plus h minus f of a, right? And that works out better this time, I think, because, well, the previous one, it was quadratic, so it's easy to see how to factor, right? This one's cubic, so I'd have to like factor a cubic. There are special form trinomials that could work for you, but it's just easier to do the h goes to 0 approach. And so there it is. This is f of a plus h. That's f of a. And when you expand these, you get a plus h cubed expands to a cubed plus 3a squared h plus 3ah squared plus h cubed. A plus h squared is a squared plus 2ah plus h squared. And then, of course, I've got my 45 times a plus h. Now, the a part here, this guy, and that guy cancel with the f of a terms over there, leaving us everything having a residual h. And then I factored the h out like so, right? So before I had 3 times 3, which was 9 squared ah. That 9 squared ah, I took the 9a squared, it's here, I factored the h over here. This 3 times 3 is 9ah, so that's supposed to be a 9. But I've got actually 9ah squared, so I took one of the h's and factored it out here. Then I had 3, hey. Oh, I lost track of myself. Okay, they're there. And then this was 3 times h cubed. I factored the h out like that. Then this 3 times 2 is minus 6a. And again, I factored the h out. 3 times 2, rather 3 times h squared. Factored the h out, gave me 3h. And then finally this 45 over here, I factored the h out. And of course, there's an h all the way over here and all the way down here, so I can cancel those. And it just leaves me this, which then when we put in h equal to 0, we get 9a squared minus 6a minus 45. There you go. That's the derivative of f of x equal to 3x cubed minus 3x squared minus 45x. Now, if I say calculate the derivative at a of this function on the test, and I don't say to use the limiting, and I don't say use the limit definition, should you use the limit definition? Say, no, don't do that, right? Like, what's the easier way to do this problem if you're not set h? How about, come on. Stay. Yeah. All right, well, so we had what, f of x? What was it? 3x cubed minus 3x squared minus 45x, isn't that right? So if I'm just calculating the derivative at a, I could do this. F prime of x is d dx of what? Then I could use linearity to pull out the 3, pull out the minus 3, pull out the 45, and then do the power rule. So that's 3 times 3x squared minus 3 times 2x minus 45, which is what? 9x squared minus 6x minus 45. That is f prime of x. So that tells me then that f prime of a is 9a squared minus 6a minus 45. Now, of course, that's the same answer that I just derived following the instructions in this problem. But as you can see, that's easier than going through the limit quotient, right? So we have to follow instructions. And you also have to know what's the right tool for the job, right? And so if I don't tie your hands and say you have to do the limit quotient, don't do it. Use the things that we know, as I talked about Monday. Linearity, pull out a constant, power rule, derivative sine, derivative cosine, derivative exponential. That's all we know at the moment. After test 1, we'll learn product and quotient and chain rule, okay? So this is how I would want any student of calculus to calculate the derivative of that function if I didn't, put blinders on them and force them to go through the definition, as was the case in this homework problem. I do think there's value in going through the homework problems, though, because they sharpen your algebra skill, right? And that's one of our larger goals in here, is to become masters of algebra, not just, casual users of it, but by the time you get done with calculus, you should be so good at algebra that it's effortless, all right? And every problem you do like this gets you a little bit closer to that goal, right? Everybody who takes algebra, even students who have an A in it, they still have a lot of things to learn. I speak for myself. I didn't completely finish learning algebra until I was in differential equations, probably. For me, it was the calculus sequence and then some, where I felt I finally got to the point where I felt okay, there's no more algebra for me to learn. Standard algebra. Now, that's still not true. If I was to dig into the right book from 1890 or something, I could still learn algebra. There are techniques in algebra which have been lost because we don't teach them anymore. But anyway, now the rest of this problem is horrible. And so the finding the turning point here is just atrocious. It's an unfortunate, it's not impossible, it's just not pleasant. Because, so a turning point is going to be, graphically, that's going to be a place where you have a horizontal tangent, right? Horizontal tangents happen at the top of mountains and the bottom of hills, or in the valley or at the mountaintop. You have a horizontal tangent, and that would be what we call a turning point. So that's yet another algebra problem. We have to solve f prime of a equal to 0. Now for this one, that means solving this quadratic, 3a squared minus 2a minus 15 equal to 0, which sadly does not factor nicely. So I decided to use the quadratic formula because there's really nothing much to be gained by using another method. And that gave me 2.59 or minus 1.93. And so those are your turning points. And so once you know where the turning points are, you can kind of make a more intelligent graph, right? Well, so you can factor x out. So you know that there's a 0, the original function, you know that there is an x-intercept at 0. And you also can use the quadratic formula to find out that this has zeros at 4.41 and minus 3.41. So this quadratic formula got me this guy and this guy. And turning points are here and here. The 54.1 and minus 84.6 come from plugging in these numbers into the function. All right, so it's a mess, but Now, I try to avoid these kinds of like ugly decimal things on a test. Like on a test, I try to make the turning points, I would try to make them come out something nice, like, you know, 1, 2 integers, or at least like nice fractions or something. But in the homework, sometimes things get messy, but that's okay. You can also use like Wolfram Alpha or other, you know, websites to help you calculate, crunch the numbers and such. Or you could use your calculator and the quadratic formula. It's kind of up to you. So what's the big idea in problem 52? Turning point is where the derivative is 0, right? Turning point is where the derivative is 0, if there is one. Now this here, I've asked you to calculate the derivative of 1 over x cubed at a, right? Assuming a is not equal to 0. So what did I do? I did the, again, I said use the difference quotient, right? And I think I also said, oh, goodness gracious. I don't know how people use this thing. And I also said, I said find the slope of the tangent line to y equals 1 over x cubed at a comma 1 over a cubed for a not equal to 0. So that's just like another way of saying find the derivative at a, right? The derivative at a is the slope of the tangent line at a, right? So any questions about the steps here? What's that? Go over, okay, yeah. So I decided to use the x minus a format for the difference quotient for this one. And once I do that, well, f of x is 1 over x cubed, right? F of a is 1 over a cubed. Then I don't like big fractions like this. It's just, I don't know, it's easier to write this as 1 over x minus a times the numerator. And then, so I did that. Now 1 over x minus a, the numerator, what did I do here? I cross multiply, right? I put a cubed up here, I put x cubed up here, and I made that common denominator of x cubed a cubed. So making a common denominator combines these fractions. The reason that I didn't just plug in a is why. Like, why don't I just plug in a from the start? It's because it's type 0 over 0, right? All of these difference quotients of tangent, you know, the slope of the tangent line is intrinsically a problem of type 0 over 0. So I can't just plug in the limit point for any of these. I have to work out the algebra, right? The limits we did before we talked about derivatives, some of those you could just plug in the number, right? Others you had to work out the algebra. Well, now that we're doing difference quotients for functions, it's always type 0 over 0. It's almost always you have to do some kind of algebra, almost always. Okay, so made my common denominator. And then at this point, I factored a minus out because I like to think of this as x cubed minus a cubed. X cubed minus a cubed is equal to x minus a times x squared plus ax plus a squared. This is a known identity from algebra. This is the special form trinomial. Do you guys know the special form trinomials? Maybe not. I feel like I mentioned them at some point, but I understand, you know, me mentioning something doesn't equal you learning it. So I will say it again. So there are two of them. Here's one, a cubed minus b cubed is a minus b times a squared plus ab plus b squared. So that's the one that's in play here. We basically have this as being identified as x cubed, and this one is the little a cubed, right? So that's equal to x minus a times x squared plus ax plus a squared. And of course, you can try multiplying that out, And you'll see that, in fact, this is an identity of algebra. So it's something you should know. Yeah. Yeah, for like pretty much, I mean, I can tell you everything I know about cubics in a minute here. I know this identity. I also know if you, instead of have a cubed plus b cubed, there's also a nice formula. Like a cubed plus b cubed. It's almost the same, but it's a minus b. A squared minus ab plus b squared. It's almost the same pattern. You can actually get that from replacing b with minus b in the identity above. There's also that. The other thing I know is this, a plus b cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed. That's another thing I have in my mind ready to use for cubics at a moment's recall. Now this comes from Pascal's triangle. You know, this is 0, 1, 2, and this is the third. Like if I had the next line, that gives me a plus b to the fourth power. It's a to the fourth plus 4a cubed plus 6, that's a b, plus 6a squared b squared plus 4a. Every time b gains 1 and a loses 1, plus a to the fourth. So, I mean, I think it's healthy to know Pascal's triangle and be ready to like expand a plus b to a power. This comes in handy here and there. What else do I know about factoring a cubic? It's a pain, generally speaking. Like, I mean, if there happens to be no constant term, we can factor x out. I think that happened in the previous homework problem. Yeah, there was a 0, x-intercept at 0. That's because we could factor an x out of that one. That's about it. I mean, generally speaking, factoring a cubic is a real troubling problem. It's one of the reasons the intermediate value theorem is so interesting is because it can show us that there exists a 0 of a cubic even if we can't factor it. If we can show that there's a place where the cubic is negative and then it changes to positive, then intermediate value theorem says somewhere between that there has to be a 0 for it, at least one. So we're, you know, that's pretty much all I work with. As far as I know, there are no other well-known secret formulas outside like math Olympiads in Asia. What those people know, I don't know. I don't know. Okay, but anyway, so we factor that, right? And then why did we do that? So, general point of advice. When you're doing the x goes to a limit, you're trying to somehow factor x minus a out of the numerator. Somehow f of x minus f of a has to produce an x minus a term that's going to cancel with the x minus a in the denominator if the limit's going to work out. So you're not really completely in the dark about the factoring in these problems. You can anticipate that there should be like an x minus a. Or if we're calculating the derivative at 3, you'd anticipate there being an x minus 3 term. If you were calculating the derivative at minus 1, you'd expect there's an x plus 1 you can factor out. Right? So you're not alone in the factoring. You have, if you think about what you're doing, you can anticipate where the algebra is going. That's very powerful, right? If you know a polynomial and you already know that the factor has to be something, that's a much easier algebra problem than just factoring in the dark. Anyway. So this cancels with that, and we're just left with this stuff up here, x squared plus a squared. divided by x cubed a cubed, then at this point it's no longer indeterminate. We can plug a in. So we get a squared plus a squared plus a squared divided by a to the 6th. There's a minus out front, so that gives me minus 3 over a to the 4th. Right. Which should be completely unsurprising to you now if you have absorbed the power rule, right? What did the power rule say? d dx of, what was it, 1 over x cubed, right? That's d dx of what? X to what power? X to the what? Minus 3, right? This is x to the minus 3 power. Power rule says that is n x to the n minus 1 with what? N equals to minus 3. So this is minus 3 x to the minus 4. Right? So in other words, f prime of x is equal to minus 3 over x to the 4th for f of x equals to 1 over x cubed, right? Thus, f prime of a is what? Minus 3 over a to the 4th. So if I don't make you do the difference quotient, the power rule is, again, much, much easier. Right? So, if I say to use the limit definition and you use the power rule instead, I'm only going to give you about like 20% credit because it's not the solution and it's not, I mean, I really do want you guys to figure out how to do this kind of algebra, right? And on the test, the questions I will ask you will be very similar to the ones I've already asked. So if you understand how to do the algebra for the ones in the homework, you should be able to do the test just fine, all right? Now, problem 54 is kind of an interesting problem. In problem 54, I have you doing a variety of things, but the basic idea here is to illustrate the chain rule. So g of x is 2x plus 3. So I first of all calculate g prime of 1 because the problem asks me to do that. When you do g prime of 1, we do g of 1 plus h minus g of 1 divided by h, right? That's 2 times 1 plus h plus 3 minus, well, 5. So this 5 and the 5 over here cancels, and it just leaves us with 2h over h, right? And so the h's cancel, and we just get 2, which is not surprising, right? Because f of x equals 2x plus 3. This is, the graph of that is a line with slope 2. So a line with slope 2 has the derivative of 2 everywhere because the slope of a line is 2 at each point. So that's g prime of 1. And then I said also calculate f prime of 5. So f prime of 5 over here. And what was f? Oh, I forgot to move my camera back. Anyway. It doesn't really matter. It doesn't work. Anyway, f prime of 5 is this. And so f of 5 plus h minus f of 5. F of x was 3x squared, right? F of x was 3x squared. So I do that. I get 25 plus 10h plus h squared from that. And then 3 times 25 from this. So the f of a terms cancel. In this case, f of 5 cancels with f of 5 over here, like that. And it leaves us 3 times 10, which is 30, and 3 times 8 squared. I factor the h out, I cancel it. That gives me 30 plus 3h. And then that gives me f prime of 5 is 30. And then part C of the problem said, okay, and also calculate h prime of 1. Now, h of x was formed by the composition of g of x and f of x. It was, h of x is actually f of g of x. So it's 3 times the formula for g of x squared. And so that actually, when you work it out, it gives me 12x squared plus 36x minus 27. And this time, I did the limit as x goes to 1, I guess just to be different. And so what do we expect? Remember I just told you? We should expect we can factor out x minus 1. If we're doing the difference quotient, we have x minus 1 in the denominator. We ought to be able to factor out x minus 1 in the numerator. And I think if you just looked at 12x squared plus 36x minus 48, and I said, everyone sees x minus 1 as a factor of that, you'd probably be like, I'm not part of everyone, so I don't know what you mean, right? I mean, yeah. So I pulled the 12 out because there's a common factor of 12, right? So I might as well get the 12 out. That gives me x squared plus 3x minus 4. Then that factors to x minus 1 times x plus 4. As I said, there's an x minus 1 in there. It cancels. We're left with x plus 4. Plug in x equal to 1, we get 1 plus 4, which is 5. So 12 times 5, h prime of 1 is 60. And then part D asks you to explain what the connection between these numbers is. All right? And if you didn't see this and you did the homework, like I would not be terribly disappointed in you if you didn't see it. This is really kind of a discovery question. I'm completely sympathetic to people not seeing the pattern in the numbers, all right? But this is the interpretation that I was ideally wanting you to find, was that h prime of 1 is f prime of 5 times g prime of 1, because this was, what was it? 2, and this was 30. No, that was 2, this was 30, right? And that's because f prime of 5 is actually f prime of g of 1. G of 1 is 5. So f prime of 5 is f prime of g of 1. And then this is g prime of 1. This is a specific instance of what's called the chain rule, which we will prove in more generality after test 1. But problem 55. I asked you guys to, come on, prove that the derivative of sine was cosine, right? And so I did the x plus h minus f of x plus h minus f of x divided by h limit quotient. And so sine of x plus h is sine x cosine h plus cosine x sine h. This is the adding angles formula for sine. And then that gives me these two limits. So I pull sine x out of this and that. That gives me cosine h minus 1. I pull cosine x out of this, and I'm left with sine h over h. And we worked out in class that this limit is 0 and that this limit is 1. By looking at the triangle, looking at the circle, the unit circle, and looking at the triangle superposed in the unit circle, we derive those somewhat geometrically from almost a squeeze type argument. But anyway, we know this is 0, we know this is 1. If I asked you to prove that the derivative of sine was cosine, or that the derivative of cosine was minus sine on the test, you're allowed to assume that it's known that this limit is 0 and that limit's 1, right? And typically in the statement of the problem on the test, I would actually put in the statement of the problem, it's known that this is that and that is that, you know. Yeah?
I was going to ask, so if you were to write it out, cosine, so with the sine known as 1, or would you rather us work it out? I'm just asking.
If I would what? I just didn't.
Something like how you said if you were to put that on the test, and we would just write, it is known that cosine is 0 and sine is 1.
Mm-hmm.
We wouldn't give you the credit, right? Or would we have to
Oh,
figure it out?
this? I mean, if you just tell me, prove d dx sine x is equal to cosine x, and you just tell me it's known that the derivative of sine is cosine. No, I'm not going to give you a lot of credit. Like, I want you to show me from the limiting quotient why it's 0. No. On the other hand, I'm not going to take off points if you don't derive the adding angles formula for sine for me. I haven't done that for you either, right? It's an exercise in analytic geometry. You can show that the sine of a sum is the product of sines and cosines like so, right? So let's see here. In terms of things you're responsible for giving proofs of on the test, this is one of them, right? If it's been a homework problem, it could be a test problem. So if you look back at the homework, I've asked you to prove maybe about 4 things, maybe 5 things in the homework. If I was to ask a quote-unquote proof on the test, it would probably be one of those. Either, derivative of sine is cosine, or another one. I think we have another one coming up, right? Like, this is kind of a proof question, right? Now, I did this in class. I did it a different way, I think, but this is how I did it in the homework when I saw it. So I'm supposed to show that if a function is differentiable, then it's continuous, right? And so differentiable at A implies continuous at A. The proof of that, here's a potential way you could argue. I say, okay, well, first of all, we know that this limit is given. It's equal to f prime of A, right? And so what I then did was I say, okay, well, that means that 0 is equal to the limit of this minus the limit of f prime of A times x minus A over A, right? So this is just an identity. F prime of A is equal to the limit as x goes to A of this. So I'm just working backwards. And once I know this, well, that gives me, making common denominator, that this limit is 0. And I can pull out the, I can put that over there as well. This has limit 0, that has limit 0, so of course the product also has limit 0. These both exist. When I multiply these, though, something nice happens in that the x minus a's cancel, and I'm left with the limit of this must also be 0. But if the limit of this is 0, then I can calculate the limit of f of x as x goes to A by adding 0 and then noticing that I've got 2 pieces, one of which goes to 0 by star, and the other which is, well, equal to f of A because of, oh, this is just a constant. The limit of a constant is the constant. And then that's exactly what I want. I want the limit as x goes to A of f of x is equal to f of A. That proves continuity of f at A. Now, I think the way I argued it in class was easier, but this one, I think it's more important for you to know the result than the proof. Like, it's important for you to know that if a function is differentiable, then it's continuous, all right? The converse direction is not true. Can you give me an example of a function which is continuous at a point but not differentiable? What's our go-to example of that? This guy, right? F of x equals the absolute value of x. That's a function which at 0 is not differentiable because it has a kink or a corner in the graph, right? But it's everywhere continuous. There's no jump in the graph. The limit as x goes to A of f of x is equal to what? It's equal to f of A for every x in the domain. So for every A in the domain. All right. So the other proofs I more had in mind as possible test questions were probably like this one. 57, show that you can pull a constant out of the derivative. So given that f prime exists, we can calculate the difference quotient for c times f, and then pull the c out. But this is exactly f prime of x, which gives you c times f prime of x. So this proves that the derivative with respect to x of c times f is equal to c times the derivative of f. Or this one down here, the derivative of the sum, we can look at the limit quotient for the sum, right? And then break it into a sum of these two guys, and then these separately exist because these are the difference quotients for f and for g respectively. So to my mind, problem 58 is a much better test question for the test than like that continuity one, because the continuity one's kind of like, I'll just say this one. I will not put the differentiable implies continuous proof on the test. We'll just rule it out to focus your attention elsewhere. I actually find a slightly better way to prove it after test one, so let's just put it off for now. This one, on the other hand, I think is a decent test question. You know, show that the derivative of the sum is the sum of the derivatives. This is how we prove it. Okay? Now, probably 30% of your test will be stuff like this. All right? So I'll make about 30% of the test not based on limits, but just based on using the power rule, linearity, and pulling the constant out. All right? I want us all to have that skill going forward in the course. So as we're, after test one, looking at product quotient chain rule, we already have power rule down real good. All right? So I'm hoping this achieves that goal for all of you. So each one of these, what we do is, you know, pull the numbers out that we can, and then we differentiate the resulting power functions, right? So like this one, 2x cubed plus 7x, pull out a 2, right? Bring the 3 down, 3 minus 1 is 2, so that gives us 3x squared, and then there you go. This one here, I pull the 2 out, I pull the minus 7 out, derivative of cosine is minus sine, derivative of sine is cosine. Yep.
That's where I got confused
Uh-oh.
while I was doing mine. So, is it that rule that that cos should be sine negative cosine?
The derivative of cosine is minus sine, yeah.
So it's a rule.
It's a what?
Is it that rule?
It is a rule, yeah. Unless I say prove it. In that case, you have to go back to do like the earlier homework problem, we proved it with the limit quotient, right? But unless the words appear in the problem show from the definition of the, you know, the definition of the derivative involving limit quotient, by all means, don't do it, right? You know, similarly, there's a more basic thing, right, than limit laws. We started with epsilon deltas. Remember that? Spent a little bit. What was the one epsilon delta problem I said could be on the test was what? The linear case, right? Which you had a homework problem like this. We'll go back to it in a second, but let's finish these first, yeah. You are allowed to bring a sheet of notes. Oh yeah, your sheet of notes definitely should have the power rule on it. I mean, if I were you, I would put the proofs that I threatened to ask on there. Yeah, you can put examples. You have 1 page of notes, so whatever you can, you know, fit on 1 page. Is what? You can do what?
I can see it.
You can't see because it's red.
Like I wrote
Oh yeah, just like that, yeah.
So basically, like a list of rules.
Yeah. Like a mathematical security blanket, you know? What's that?
I was telling them I'll get it better now. Like the D over DX, like the X, that rule,
Mm-hmm.
this stuff right here, I get this.
Yes. Good. Right. And
Well,
you're starting.
Because I think I kept plugging in for f of x, I kept taking that as just plug in x plus a, and not to plug in like what f of x is equal to. I think that's why I was getting messed up.
Yeah, I mean, there's some pitfalls here, right? Some people get tempted to think that the ddx is actually like an algebra step, in the sense like you're dividing by dx. That's not that. I mean, it's a notation for the differentiation process.
Maybe you should put like a little note or something like, hey, take out equal or something. It might make it kind of
Well, yeah, like I said, I'm going to make 30% of the test like these problems, all right? At least 30%. I might have another problem, which isn't literally like these, but it's something like find the tangent line to a function, right? But I don't force you to use the limit to do it. If you go back, I've had questions where I said find the equation of the tangent line, right? You could go back, and some of those you could use the power rule and linearity to find the derivative. There have been a few problems that we've done, though, that you only could do the limit quotient at this point because we don't have the rules of differentiation to do them yet. Like the 1 over the square root problem, or the x over 3x minus 6 problem. Like we can only do limit quotient on that one at the moment. Those are in mission 3, I think. So here we're up a creek unless we know algebra, right? So 3x times x cubed is 3x to the 4th, and 1 times x cubed is x cubed. So I multiply out, I get a polynomial in standard form, pull the numbers out, and then use the power rule in each term, and there it is, right? These aren't bad once you get going on it. But we need to do more than just get going on these. These need to be effortless for you. You need to be able to do these like you tread water, right? Like if you need to do these for a day, just continuously, like you should be able to do it without getting tired. You know what I mean? Like you get so bored of the power rule that it's second nature. Derivative of x to the 7th, 7x to the 6th. Now the derivative of the exponential function is just the exponential function again, so there's that. And don't say I didn't put any real world applications in this course. Here's one right here. I said the position of a ninja. I mean, because if you're going to think about it, position of something, it might as well be a ninja. You have a ninja at 3t squared, at x equal to 3t squared plus 2t plus 1, I think. I said find its velocity. So the velocity relates to the position. Velocity is the derivative of the position, the instantaneous velocity. And so this one, I get 6t plus 2. And then I asked us to find the instantaneous velocity of the ninja at time 1, right? That means to calculate x prime of 1, or v of 1, because v is dx dt. And so v of 1 here is 6 times 1 plus 2, which is 8. And that's it. Would you like a problem like this on the test? Right. Right. Now, what else can we do in physics? How about acceleration? What's acceleration? Acceleration is the second derivative of position, right? What would the acceleration of the ninja be? I didn't ask that in this problem, but I could have. The acceleration would be x prime prime. X prime prime here is what? What's the derivative of the velocity with respect to time? Well, yeah, let me write it out. What is d dt? Well, dv dt, right? d dt of 6t plus 2. What's the derivative of 6t plus 2? 6t t dt, right? Well, what is d dt of 2? It's 0, right? Very good. I like that. There was no hesitation. Last derivative constant was, you spit back at me too. I mean, wait a minute, no. 0. That's good. Much improved. d dt is what? 1. Mm-hmm. So what's the acceleration? Where'd the t go? Well, that's this. That's the. I mean, I could write it d dt of t if you want, but we use this as a notation that we use. You know, d dx of f of x is df dx. These are like, this is the notation that people use. And since we're people, we're going to use it. Yes, it would just be 6. 6 what? The answer is 6 ambiguous units because your instructor didn't bother to tell you whether this was in seconds, years, and whether it was in feet, meters, centimeters, astronomical units, cubits. Right? I didn't fix any system of measurement units. So Um, haha. So I know some of you guys have been at intermediate states of understanding as the homework has confronted you, right? Like maybe you weren't quite ready for the homework when it was due. But in retrospect, if you go back and look at it, I hope you can understand every problem. One of the things you could do would be to go back to the homework blank and just try to work a problem, right? If you're completely lost, that means you need to look at that some more, right? Now the solutions are posted, right? I have answers to every homework problem written out. And I would encourage you to look at them. And don't be like me. Focus on the ones that you don't understand rather than the ones you understand. When I study, I have this very bad habit sometimes of just looking at the ones I understand most, Hey, come on. This is a little bit challenging because I don't have I can only look at the big screen. I have nothing to look at up here. All right, well, can I open it? Thank you. So I know some of you got this problem wrong. I think almost everyone needs to look at this problem 37. How do I choose C to make this function continuous? Right? At 2. Well, at 2, for it to be continuous at 2, I need the left and the right limits to agree, right? So the left limit, I have to approach x from the values less than 2. For values less than 2, I'm using the upper case. I use cx minus 1 as the formula, right? So the limit as x approaches 2 from the left is the limit as x approaches 2 from the left of cx minus 1. Which we can plug in, we get 2c minus 1, right? On the other hand, the limit from the right, and by the way, did I write limit equals? No, I never, ever have written limit equals. I write limit of something equals limit of something else. You'll never see like a naked limit in my work. But you guys have some bad habits, which is write limit equals stuff. Right? This is not proper. It will get you into trouble. Same for derivative. I've seen some of you writing d dx equals stuff. Right? That's not how it works. We do d dx of some expression equals another expression, right? The d dx is always something that acts on something. It's an operator. The limit is always something that acts on something. You don't just write acting on something equals something unless you're in a more esoteric context than where we are right now. Anyway, I shut up. So here, from the right, we use the right formula. And the right formula is 4c times x minus 2 over x squared minus 4. That factors. We cancel the x minus 2's. And then we can plug in 2. We get c over 4. So for this to be continuous, I have to have the double-sided limit at 2 exists, which means this must be equal to that. And then I do algebra, and I think I got c equals to... Now, listen, it's always possible that I make an algebra mistake in my solution. So if you're following along and then you feel like there's an algebra mistake at the last step or something, if you're even if you're like only 20% sure I'm wrong, send me an email. Let me double check it for you also. I do not mind. And I do make mistakes sometimes, right? And there's only, 5 students here? So odds of you being the first person to find the mistake are much higher in this class than it would be if I had 40 students. There might be a mistake there. I don't have like a secretary to check my work or something. I try to do it right, but I am human. So 8c minus 4, and so then I subtract c to the other side. I get 7c equals to 4, so that gives me c is equal to 4/7. All right, so before I just start going to other problems, Are there any particular questions you guys have? I sometimes ask for the definition. I'll be like, define what it means f prime of a to exist. Define what it means for a function to be continuous. State the intermediate value theorem, right?
So we have to know the law.
Know the what?
We have to write the law. Law.
Yes.
We have to define the exact.
I might ask you to define continuity, yes. I do give you a sheet of notes, though, so you could put them on there. Let's see here. So there's this problem, right? Show that this function defined below is discontinuous at 2, right? So what do? I show that the limit from the left is -3 and the limit from the right is 3. Those are not equal, therefore it's discontinuous, right? There's these sort of symbolic limit problems. They're actually very easy. Intermediate value theorem. If we have an intermediate value theorem question, what are the critical ingredients for an intermediate value solution? Number one, we have to identify which function we're going to use the intermediate value theorem on, right? In this case, the function is identified to be the square root of 4x minus the cube root of x over 4, right? Step number one, which function are we using? Step number two, verify the claim that the function's continuous on whatever closed interval we're looking at for the intermediate value theorem, right? That's a necessary assumption of the intermediate value theorem is the function's continuous. If the function's not continuous, we don't get to apply the intermediate value theorem. It's not true. Discontinuous functions can jump over values, right? They don't reach every intermediate value between f of a and f of b, necessarily. And then also you have to produce values for the function at the endpoints, right? Like f of 0, in this case f of 3. The 0 and 3 are important in that the number we're interested in, 1, is between them, right? And then, so by the intermediate value theorem, since 1 is an intermediate value of f of 0 and f of 4, that implies that there exists a c on 0, 4 for which f of c is equal to 1 in that. This means there exists. I'm sorry, that's a shorthand. There exists. So that's just an abbreviation of this phrase. The other popular mathematical abbreviation is this. This means for all. If you see this one, this means there exists uniquely. I capitalized the uniquely for like shouting because exclamation point. Sorry, it's a stupid pun. But anyway, I don't think that's him up, but mathematicians left to their own devices will just throw out there exists exclamation point and think people know what they're talking about, but yeah, that just means there exists. So. All right, let's get out of here. Let's see if there's anything else I want to talk about here. I'm sorry? Continuous and discontinuous? Like what about it? To a problem. Ah. Oh, man.